Good evening from Dhaka, Bangladesh. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. We are arranging a lecture series on X-ray crystallography and solid-state chemistry. Today is the 21st lecture of that series. Well, we discussed a lot about sphere of reflection, limiting sphere, and about other aspects of data collection, how we collect data. But then we have to also take into consideration that whether we need to have all reciprocal lattice points intensity in our data. We will see that this depends on the symmetry of the crystal system. So when we will see that they do not represent independent observation. All limiting sphere data do not represent independent observation, and that is because of symmetry of reciprocal lattice. Therefore, reflections having indices related with certain symmetry will have the same symmetry, will have the same intensities, and therefore only a member of the set needed to be measured. Okay, now the data we have, it depends on totally wavelength of the radiation which is used to collect data. And as we said before, that limiting sphere, therefore we can, if we use copper radiation, we call copper sphere. If we use molybdenum radiation, we call molybdenum sphere, etc. Okay, so how to take this unique data? This figure shows sphere can be considered by cutting three planes. As you say, that reciprocal lattice. This is the axis, this is one axis, and this is another axis. And here we have three planes. This is one, this is another one, and this is the other three planes. Each plane, you see, containing two reciprocal lattice axes. Okay, and therefore, if we see this observed data, and then we that one intensity observed, HKL is the reflection, equal to intensity observed, H bar, K bar, L bar. And the distribution of intensities is centrosymmetric. If it is centrosymmetric, then this relation holds good. Therefore, it is never necessary to investigate more than a hemisphere of the points that cut by limiting sphere. This hemisphere can be taken arbitrarily, but in practice, we see that this hemisphere selected with one of the planes shown in figure 1, any plane shown. Okay, now that we say that this holds good according to Friedel's law, we will see that if the crystal is having triclinic symmetry, so it is only bar 1 is the symmetry, space with 2. And therefore, the unique volume of the reciprocal space for triclinic system, we have to collect this full object. But when we go to higher symmetry than that of triclinic symmetry, then, for example, monoclinic crystals, we have a point group symmetry 2 by m. This is a higher symmetry than that of triclinic one. Then we will see that with the set of reflection, we will discuss that this holds good if we have these relations. You see, intensity, observed intensity of HKL is equal to observed intensity of minus H, minus K, minus L, and this relations. Okay. So, in case of monoclinic, the hemisphere will use this one, this octet, this data will be taken, and rest will be taken care of by symmetry. And you will see that if the symmetry related one will have the same intensity. The reciprocal lattice, symmetry related one will be the same intensity. So therefore, we will see that higher the symmetry, the octant we will measure the data. For example, if it is orthorhombic, the symmetry point symmetry is m. Therefore, this the only octant we use collect data is followed by this relation of Friedel's law. If we have more higher symmetry, let's say triclinic, let's say tetragonal, then cubic, we will see that we can even collect less than an octant of data, and the rest will be taken care by the symmetry operations. So, which are the intensity data we will collect? Here I mentioned about triclinic, monoclinic, and orthorhombic. What are the intensity data we will collect, and what indices we will collect the data? And the above rules, these rules holds good for general HKL value. You see, and we have some special cases. What is the special cases? If we have one or two of these, HKL belongs to a zero. So if it is zero, then that represents this is a special case. I mean to say again, HKL value is a general one, but when we have zero, so let's for 0KL or 00L, and then these values are special cases of value, and then this will follow suit. Or which are the data we to take. Okay, now we go for them. Now we have the data. Next point, we have to, this is an observed intensity data we have collected. And depending on the symmetry, we have collected the octant or whatever number of observable intensity, we have collected it. So this collected data is the raw material for the determination of 3D structure of the particular crystal. This is the raw material. The next step is that we have to reduce this data. And then these raw materials we have got all information needed for final structure determination of a crystal. Now, since we have to reduce this data, we have to very skillfully extract the observed intensity data. Very skillfully, I said. And therefore, what we do, what we mean to say that let's a crystal be taken. One can take a already determined structure and then process all these things step by step and see that whether he or she can reach to those structure, already known structure. So that is that what is one can call skillfully extracting the raw material, observed raw material, that is observed intensity. And that is termed as data reduction. Okay, once we have going for data reduction, what we get, the most important quantity we get from observed intensity is structure factor modulus. That what we need for our three-dimensional structure determination. And this is symbolized like this, structure factor, or we call it structure amplitude. So how it is related with observed intensity? It is directly proportional to the square root of observed intensity. So that one we call observed structure factor modulus. Now then, what happened? What we get? We get an observed data, observed structure factor modulus. Then how can we determine the structure from here? Well, once we have the space group, when we go to the space group, we can see that we have the atomic position also given in that space group position. spatial position, general positions are given. From there, we can theoretically calculate the structure factor modulus, which we call FC. That's what theoretical. Okay, once we have theoretical structure factor modulus, this is also used to calculate electron density maps. And once we get electron density maps, we also get the position of the atom. Atoms are determined from that electron density map. We say then it is like this, that we have observed data and we have space group, and we go to the space group, and from that data we can from the space group and the position we can calculate the structure factor calculus, and then we compare this. Okay, then convert this intensity data to structure factor, as I said, and that is data reduction program. We have many data reduction programs, and we use those data reduction program to convert intensity data with this observed data. But then it depends on number of factors. So primarily geometric factor that are related to individual reflection, and also the apparatus, which apparatus we have used to collect the intensity data. So these are the things we have to take care of very carefully. And then we come out, we can rewrite this formula. We can write F structure for modulus scale, and which is proportionality constant. We have equal to a proportionality constant and observed intensity HKL divided by LP and square root of it, is square root of this one. So K is the proportionality constant, P polarization factor, L Lorentz factor. We go to, then what is polarization factor? You see, polarization factor, we can define this as 1 plus cos squared theta 2, 3 by 2. Okay, now we can see that this polarization factor is a function of 2 theta. So if it is a function of 2 theta, it is independent of method of data collection, unless we use crystal monochromator. We have been discussing about this, what is crystal monochromator, etc. Now we go for Lorentz factor depends on what this Lorentz factor depends precisely on measurement technique. What sort of measurement we are doing, how we collect our data. For the equi-inclination Poisson-Berg, we have Lorentz factor is equal to sine theta by 2 sine 2 theta into sine squared theta sine mu, which is square of this square root of this term. Okay, this mu is the equi-inclination setting angle. So zero level reflections, this equation reduces to L is equal 1 by sine 2 theta. As this is applicable to zero level Poisson-Berg photographs, zero layer reflections, rotation and oscillation photographs. And also if we collect diffractometer data, that is usual 2 theta and omega scans. Okay, now that the K of this equation K, which we have written earlier, okay, this equation depends on crystal size, beam intensity, and number of fundamental constant. In initial data reduction, we can omit this K. And then we come up to this, the real structure factor, and then K prime, and structure factor observed, which is equal to this. What is then the scaling between this observed and real structure factor can be taken into consideration later stage of comparison, not just at the beginning of the calculation. You can take into consideration later. Okay, next slide. Here we are talking about electron density. What is it? It is a scalar quantity And it is probability of finding an electron in a very infinitely small space around an atom or molecule. The unit of it is electrons per cubic centimeter. This concept, electron density concept, is very much used in chemistry and material science. What? Why? Why? We can get this high density region typically found near atoms or bonds. So electron density mapping is a technique in crystallography that creates three-dimensional plot of electrons that are concentrated within the crystals. If we analyze this, what we get, we can get the location of atoms, visual molecular structure, chemical bonding, interatomic positions, atomic position, etc. And that helps us to predict the molecular stability, acidity, basicity, and how a molecule will behave in chemical reactions. This expression, electron density expression in the unit cell, is given by this equation. One can derive this equation step by step. So I didn't show that equation derivation. What I am saying that what we can do from electron density mapping. And here is a electron density mapping in two dimension. From here, we can find out the atoms positions and bond length, etc. bond length. So that is a very important entity of electron density mapping, which you use in three-dimensional structure determination. Okay, so in the application of electron density expression, it's difficult arises. Why? The coefficient of series, this series coefficient, because of this. And it is not merely the moduli of the structure factor, it is also moduli plus observable, non-observable phases. So this is a compact equation of this density mapping expression. But actually in computer, we use this equation to calculate this electron density mapping. So what we have to do, we have to remember before we calculate electron density map, what is necessary? It is necessary that we assign each modulus plus a phase. And hopefully this phase is more or less correct. And then we are able to calculate electron density map. Okay. In last couple of lectures, especially the 20th lecture and 21st lecture, we have been talking about basic concept of 3D structure determination of single crystal. And that basic concept we need to have in mind and then do practicing and get how we determine the structure of an unknown compound. Okay. Now, what I'm showing here, you see, this is a X-ray tube. I showed it in the early lectures. That is the window of X-ray tube. We get X-ray beam here, and this is a structure of Hussain, a zinc sulfide compound. And if we get the X-ray single crystal of this, and we get reciprocal lattice spots like this. But we have also shown or also discussed the powder diffraction, what we get here. And we also talked about that the powder diffraction is compressed in one dimension, but the reciprocal lattice point is not compressed, it's a three-dimensional reflection we get. Okay, so now we can say, if you remember intensity relationship, so intensity, structure factor squared, and Lorentz correction, polarization correction, absorption correction, scale factor, multiplicity, plane multiplicity. All we have to take into consideration to get our observed structure factor, observed structure factor. Okay, so whenever we get, let's say this is a reciprocal lattice point, okay? We are getting its intensity. We get intensity like this. And then what happened there? We have a background noise here also, background. We have to deduct this background when we are calculating the observed intensity. And there are some very good techniques what we use. And if you take a textbook, I will say, if you take a textbook, you see there are many chapters relating data reduction, what is unique data, what is how we can correct this intensity data, and then how we can calculate electron density map, and how we determine structure, and there are different methods of that. Plus, we have different programs by which we can calculate, we can determine our structure from the intensity data. You see, I probably told you that we have observed, already I told you, observed the intensity data, and then we have calculated intensity data, and then we subtract from observed to calculated and find whether the structure we can expected or resulted structures are correct or not. We are taking an example of iron oxide, Fe3O4, and its intensity data. You see that this is black spot. These are observed intensity data, and of various reflecting planes is 220 and etc. And then we can calculate this knowing the space group and things like it. And you can also calculate the powder diffraction data. And that is what is a reddish red one is the calculated powder. Then we compare these two, and the difference between these two is shown here. This one, difference between these two. So with looking to this data, we can at least say why it is, or how the structure has been determined and how good it is. Do remember that it is very difficult to determine three-dimensional structure for powder from powder pattern. As small molecules may be determined with the help of rate-well refinement or so. But in case of bigger molecule, we need to go for three-dimensional structure determination, single crystal detector. Okay, this slides shows you how we report a structure we have determined of an unknown sample. That we need to give the empirical formula weight, temperature, which we have taken the data, wavelength, crystal system, space group, unit cell dimensions, and volume of the unit cell dimension, how many formula you need in the unit cell, and this density calculated, absorption coefficient, and then crystal size, this all, and how all, then finally we give the residual factor or residual index, or less desirably we call it reliability index or linear scale factor. So that is how it is defined, what is linear rescale factor and how we do it, the definition of this. And then also that when we reflection by reflection go for agreement between the observed and calculate ones. This is what is known as residual index. And there is the residual index, definition of residual index. A residual index, when we finally get the structure, and the residual index, if we get 0.45, it's not totally not hopeless. It suggests that probably you have to give a considerable refinement with some parameters, and then we come down to this R value. Okay, but if we get an R value in the initial stage, it is 0.35. We think it's a quite hopeful value. And below 0.25, the structure is almost correct, except for small atomic shift, you see, less than 1.1 Armstrong. and changes in thermal parameters. With this modern techniques and well-behaved structure, the reliability index of R factor is in the range of 0.1 to 0.06, even a little bit less. So here is the two-component nickel complex compound, how this structure, three-dimensional structure determination information is given. And with this information, you can report it and publish a paper on it. Okay. So this is the last slide of this lecture, that we are talking about single crystal data and data collection, crystal growth, etc. This all we have discussed. And the last section of the syllabus, which we thought that we will cover for this single crystal accelerated diffraction and accelerated diffraction, single diffraction, and the structure of solids. So last chapter, we have this structure of solids of some inorganic compounds we will be taking, and most important inorganic compounds, and structure of some organic compounds. So in this, we will have close spec structure, and other point we have to discuss. Well, thank you very much for listening this. In the next few lectures, we'll talk about structure of solids. Thank you all.